international journals. On the behalf of Government Holkar Science College, we welcome you, sir, for the lecture on the topic Experimental Characterization of Materials using X-ray Spectroscopy. Over to sir.
Thank you, Bhavna madam.
Okay.
So, very good morning,
Good morning,
to all
sir.
of you.
Good morning,
I
sir.
hope all of you are safe in this COVID-19 situation. Myself, Dr. Saurabh Dallela, Associate Professor in Physics from University of Kota. My research area and expertise is material science, especially I worked with the superconducting and spintronics materials. I hope you are familiar with the terms dilute magnetic semiconductors. DMS, these are the oxides like zinc oxide, cerium oxide, titanium oxide, stannous oxide, etc. These material offering a band gap energy of the order of 3 to 4 electron volt. The prospectus of these materials can be tailored with the doping of transition metal and rare earth cations in the host matrix. Basically, I am studying structural, electrical, optical, magnetic, and electronic structure properties. I also have several time worked with synchrotron radiation, X-ray photoelectron spectroscopy. That is, nowadays we are working with the X-rays photoelectron spectroscopy with the synchrotron radiation because it is highly polarized X-ray. But in conventional XPS systems, we are dealing with the aluminum K alpha and magnesium K alpha source. I would like to brief a little about my department. You can see the building in first slide. This building is shared by two departments, Department of Chemistry and Department of Physics. Our department is quite a young department. It was established in 2007 and nowadays offering the courses on MSc Physics, MPhil Physics, PhD Physics. We are also offering a dual degree program that is known as Integrated BS MS in Physics. We are also offering MTech Solar Energy. Our students are comprises of mostly from Hadoti region, Madhya Pradesh, Rajasthan, other cities, Gujarat are coming through a tough competition in MSc Physics. Every year around 10 or more students succeeded for NET JRF, NET LS, JEST, GATE and other competitive examination. So now I will continue with the presentation. As this webinar is especially decided to modern physics and material science, I am starting with basics of material science initially, then I will continue with the X-ray photoelectron spectroscopy. I try to discuss this presentation in very simple way on material science and XPS so that a student of PG class and research student can understand properly. However, this XPS technique is quite useful for physics, chemistry, biological sciences students, but the working procedure of XPS is closely related to physics. First, I would like to introduce about the material science. This is the outline of my today's presentation, introduction to material science initially. Then we will discuss about the classification of materials, how materials are synthesized, not in much detail, but slight indication how to make materials, and then characterization of material, and following are the XPS outlines. What is material science? First, I would like to introduce about the material science. Material science is actually investigating the relationship that exists between the structures and properties of materials. But for a material science researcher, these two steps are quite necessary for pursuing the research. First one is the synthesis of material, and second one is the characterization of material for various properties like structural, mechanical, electrical, thermal, magnetic, and optical. Materials are classified in so many ways depending upon their atomic binding, electrical properties, or on their solid construction. Solid materials have been conveniently grouped into three basic classifications: metals, ceramics, and polymers. Semiconductor and composite materials are also classified, but we all know that semiconductors are the material which have conductivity smaller than the metals, and where composite materials are, it is a mixture of two materials having best of the properties of both materials. Now, depending upon the crystalline and non-crystalline materials are further categorized into single crystalline, polycrystalline, and amorphous material. Single crystalline materials are those which you can see in first picture. The periodic and repeated arrangement of atoms is perfect or extend throughout the entirety of the specimen. So basically, single crystalline materials are those which provide the long range ordering. Polycrystalline materials are those which have small crystals, and these crystals are termed in terms of polycrystalline chemistry as grain, and they are offering the short range ordering. In between grain, there is a boundary that is known as grain boundary. Amorphous materials lack with this systematic and regular arrangement of the atoms over relatively large atomic distances. So most of the nanomaterials are amorphous in nature. Now, brief introduction about the synthesis methods for materials. As we have studied that we have single crystalline, polycrystalline, nanomaterials, thin films are also the one part that belongs to these categories. Single crystalline material, if you want to prepare, then you have to go for vapor deposition techniques like chemical vapor deposition, and other techniques are also there, but this is the most important technique. Polycrystalline materials can be synthesized with the solid state reaction method, solid state diffusion method. Nanomaterials are synthesized by two methods. These two methods are top up and top down method. In top down method, we take the single crystalline or polycrystalline material, and with the ball mill mechanical method, we crush these single crystal or polycrystalline material to the nanomaterial size. So this is a top down approach, and in top up approach, we start with the atomic level and we can generate the nanomaterials. These includes chemical methods like co-precipitation method, Sol-Gel method, hydrothermal method, etc. Thin films can be prepared of the order of thickness in the micrometer or nanometer. These thin films can be deposited by the vacuum coating method, spin coating method, sputtering deposition method, and nowadays most common technique used to deposit thin film is laser ablation method. So now, there can be many characterization techniques depending on what property you want to study. However, we don't have infinite time for our research, then we have to be selective in our characterization techniques. It should be limited. For selection of these properties and then techniques, you can consult your supervisor, teachers, friends, or other experts. Where for structural property, we can take the techniques X-ray diffraction, transmission electron microscopy, TEM, SEM scanning electron microscopy, SPM scanning probe microscopy, IDEX. And these techniques, all techniques takes a lot of time to analyze. So we have to be selective in our approach to how much extent we are going to study about the structural properties. Electrical properties we can do with the Keithley electrometer. It will gives the simple IV characteristics and dielectric measurements to study the dielectric properties of the material. For optical properties, we can adopt a technique that is named as UV vis absorption spectroscopy. This technique is very useful to study about the band gap and refractive index of the material. Raman spectroscopy and photoluminescence spectroscopy can give the impurity characteristics as well as defect concentration in the material. Electronic structure properties. This is the toughest part of the material science research. We have to use X-ray absorption or X-ray photoelectron spectroscopy, as well as we can use X-ray emission spectroscopy and resonant inelastic X-ray scattering technique to incorporate electronic structure properties. However, we have to be selective that only one technique we have to adopt for our research. That can be XAS, XPS, XES, or whatever. Your supervisor is in expertise so that you can have proper guidance. For magnetic properties, we use vibrating sample magnetometer and squid magnetometer, etc. And using these techniques, we can study the MH curve of the magnetic sample to study various properties of magnetic sample as paramagnetic, diamagnetic, and ferromagnetic properties. We can also study the empty curve using these techniques. Now I would like to initiate with the introduction of XPS technique. It evolves with the discovery of photoelectric effect. In 1887, when Heinrich Rudolf Hertz discovered the photoelectric effect. Obviously, XPS is also based on the Einstein's idea of photoelectric effect. In 1907, Ines taken the first XPS spectrum. Kai Segbahn from Uppsala University, Sweden, with Hewlett Packard, USA, produced the first commercial monochromatic XPS. And in 1981, Dr. Segbahn was awarded the Nobel Prize in Physics for the development of the XPS techniques. XPS, X-ray photoelectron spectroscopy, this technique is also known as ESCA, ESCA, electron spectroscopy for chemical analysis, and this is the name given by the chemistry people. And this technique is widely used to investigate the chemical composition of the surface, as the X-ray can penetrate the materials up to a few angstrom only, less than 100 angstrom. This technique is surface sensitive, and hence cleaning of the sample is quite necessary before starting the XPS measurement on the sample. The surface of the sample certainly be contaminated by our touch. It can be oxidized also. Water vapors may be present on the surface, and so many other contaminants can be present. But it can only provide the surface information which is of less than 100 angstrom thickness for the material. So now we all are familiar with the atom. Atom is centrally confined a nucleus which is comprises of proton and neutron, and outside electrons are orbiting around the nucleus. If X-ray is incident on one of the core electron, what is going to happen? That core electron will absorb the photon energy, and by overcoming its binding energy, it will generate as a free electron. This is termed as photoelectron with some kinetic energy, and it is detected by the detector of the XPS system. However, X-ray interacts with core electron only because we are interested to have core levels in the XPS spectra, because it contains the information about the binding energy and the atomic information are there with the electrons. The core electron responds very well to X-ray energy. Now, how X-ray is generated? If incident, in first figure you can see, if incident photon strikes the 1s electron, that will be available as a photoelectron, and it is available outside the atomic boundary. Then from 2p, because 2p to 1s transition is allowed by the selection rule, one electron is coming to fill that electron in the 1s level to obtain its minimum energy condition. then there is a hole available at the 2p side. Then by this difference of energy between 2p to 1s, one X-ray photon is also generated with this process. This X-ray photon can be absorbed by a neighbor ion, neighbor electron, this one or this one. And if this electron absorbs this X-ray photon energy, it will be also ejected to the outside periphery of the atom. But this electron is termed as OJ electron. It is not contributing to the photoelectron or XPS spectrum. So that's why XPS contains a lot of noise. So perfect XPS analysis is quite necessary. Now I am going to discuss about the photoelectric process. What is this? When an X-ray photon is incident on the material, it can emit photoelectrons from the surface of the material. The number of ejected photoelectrons are collected by the detector to generate XPS spectrum. So it is a quite simple technique which use the photoelectron, which is generated because of the photoelectric process. And the XPS spectral lines are identified by the shell from which the electrons was ejected. Like if we are talking about oxygen atom, then if one electron is ejected from the 1s side of the oxygen atom, then oxygen 1s XPS spectrum we are going to see. The ejected photoelectron has kinetic energy, which can be derived by subtracting the binding energy required for the electron as well as the work function of the spectrometer material. Following this process, the atom will release energy by emission of an OJ electron, which I have already discussed, that this 2p electron is going to occupy the position left by 1s electron, and X-ray photon is generated. That X-ray photon is absorbed by one neighbor electron to that particular electron, and this is emitted, and this is termed as OJ electron. So this OJ electron is not contributing to XPS spectrum, but OJ peaks can be seen in our XPS spectrum. So this electron, which is occupying the position or which absorbs the X-ray photon generated because of the transition from this electron, 2p electron, to the 1s level, is emitted OJ electron. It is termed as KLL, OJ electron. Okay, this is just to convert the energy released in step first by the L electron filling to core level vacancy in K shell. The kinetic energy of this emitted OJ electron is given by energy of K shell minus energy of L2 minus energy of L3, where L2 is this electron which was driven to K shell for filling the 1s vacancy, and L3 is this electron which is emitted as OJ electron. This OJ spectroscopy also constitute a measurement technique which is used by material scientists also. Now, why we are selecting the core electrons? We have already discussed that. The valence electrons above Fermi level do not contain information about the atom, where core electrons are very much local and close to the nucleus and have binding energy characteristics of their particular element. So core electron always carry the information about the characteristics of element, and hence we are interested in these core electron for XPS spectrum. The core electron have a higher probability of matching the energies of aluminum K alpha and magnesium K alpha. These aluminum K alpha and magnesium K alpha are the X-ray source which we are using in the XPS measurement. So X-ray and the electrons, we have seen that electrons are emitted when X-rays are incident on the atoms. But there are two kinds of electrons. The electrons emitted after absorbing energy from X-ray may come directly without collision, as well as with collision with other atoms electrons, which cause decrease in energy of the ejected photoelectrons, and hence these electrons which comes with the collision with other electrons, they no longer contribute to the characteristics of the element. So these electrons are contributing to the noise in the XPS spectrum. That's why in XPS spectrum, noise is continuously increasing, because these electrons are increased in number as soon as number of X-ray photons are incidenting on the surface of the sample. Now, information from XPS. What information we can get from XPS analysis? This is very important because we are using this technique for having some important information so that we can draw some results or conclude some results with our XPS analysis in research. So first thing is that we can identify the elements type just by looking at the XPS spectrum, because for most of the core level electrons, binding energies are known. The quantity of an element up to 1 to 12 nanometer, we can determine how much quantity of the element. Like if we are talking about cerium oxide, cerium is available in 1 and oxygen is available in 2 ratio, 1:2 ratio, that we can determine even in ppm and ppt also. The contaminants present on the surface or the immediate bulk of the sample. We all know that our samples are exposed to the atmosphere. That's why they are contaminated with the oxygen as well as hydroxyl group ion, and other contaminants are also present on the sample. That we can see with XPS. We can also derive the empirical formula of the material. Like if our cerium oxide is lacking with oxygen component, then we can find out that cerium oxide, CEO2, is actually CEO2 minus delta, and delta can be determined. The chemical state identification of elements in the sample, whether any change in valence state is there, that we can also determine. Like if an element can have 2 type of valence state, +3 and +4, then we can easily identify with this XPS spectrum. Binding energy of various electronic state we can identify. Thickness of different material we can identify. Also the density of electronic states. Now XPS is having a limitation. XPS can detect all elements with atomic number greater than 3. It cannot detect hydrogen and helium because the diameter of these orbitals is so small, reducing the catch probability to almost 0. So the photoelectron emitted from hydrogen and helium cannot get in the detector of the XPS, where the detection limit of the XPS is in part per trillion, and in some condition with the contaminants present, it will be reduced to part per million. Now, a few important facts about the XPS analysis. We have to irradiate the sample surface by hitting the core electron of the atom. X-ray penetrates the sample to a depth on the order of micrometers only. Useful electron signal is obtained from a depth of around 10 to 100 angstrom, and other electrons which are contributing are actually electrons after collision with other atom electrons. So they are producing the noise in the XPS spectrum only. The XPS source produce photon with certain energies. We are going to use 2 source only, Mg K alpha and aluminum K alpha, where Mg K alpha have the energy of the 1.253 kilo electron volt, and aluminum K alpha have this energy 1.486 kilo electron volt. These are used in the conventional XPS system. Nowadays, synchrotron radiation is also used for photoelectron ejection from our sample, and this synchrotron radiation is highly polarized, highly intense beam. So XPS spectrum is having quite good intensity of peaks with less noise. Normally, the sample will be radiated with photons of a single energy. It means by monoenergetic X-ray beam. So XPS measurements are always made in UHB chamber, where the pressure of the chamber is 10 to the power minus 9 to 10 to the power minus 10 torr, to avoid further contamination due to atmospheric gases. Initially, the sample is cleaned by scraping or by sputtering or by heating so that the monoenergetic soft X-ray should not deviate from its path and reach to the sample surface. And the ejected photoelectron should not have any scattering with the air molecules. That's why these measurements are always kept in ultra high vacuum. I hope all of you are familiar with the vacuum, where low vacuum is of the order of 10 to the power 2 to 10 to the power minus 1, and medium vacuum starts from this range to 10 to the power minus 4. High vacuum is up to 10 to the power minus 8, and ultra high vacuum can be achieved up to 10 to the power minus 11. The vacuum we can generate from the pump system. So many vacuum pumps are connected to the XPS chamber. These are rotary pump, which is capable to produce 10 to the power minus 3 torr order vacuum. Then we have turbomolecular pump. It is used to create 10 to the power minus 8 torr vacuum. And then we have ion pump. It is used to create 10 to the power minus 12 torr of vacuum. So ultra high vacuum is quite necessary for surface analysis. Otherwise, XPS as a surface sensitive technique we have the signal from the contaminants, and we can speculate bad about our sample. So ultra high vacuum is also useful for removing the absorbed gas from the sample. It also eliminates the absorption of the contaminants on the sample. It prevents arcing and high voltage background also. Increase the mean free path for electrons, ions and photons, because air molecules are not present in the chamber, so there will be no scattering of electrons. So this is the conventional XPS system. You can see quite complicated system, where the topmost hemispherical part is the XPS detector, and it is known as cylindrical mirror analyzer. This is the main XPS chamber. In between we can see so many. This is X-ray tube. It can generate aluminum K alpha or magnesium K alpha photon and other electronic circuitry is also connected. But nowadays these conventional XPS systems are quite automatic, and computer system can be used to control the X-ray generation, measurement of XPS spectrum, as well as detection of the XPS signal. So in this computer screen, you can see that XPS spectrum is seen. So now X-ray photoelectron spectrometer is always working on ultra high vacuum. It is used to avoid the contamination of the surface for accurate analysis of the sample. Now sample treatment in XPS chamber. We all know that as we have our sample, it is exposed to atmosphere, so many contaminants are present on the surface. As XPS is a surface sensitive technique, contaminants will produce a signal that will lead to noise and incorrect analysis of the surface of composition. That's why pressure of the experimental chamber in which XPS spectrum is recorded must be of the order of 10 to the power minus 9 torr, not less than that. How to remove this contamination? Before introducing the sample to the experimental chamber, we have a introduction chamber before that. This introduction chamber is having a pressure of the order of 10 to the power minus 8. With heating and oxygen bombardment, we can remove the hydrocarbon from the sample surface. Sample surface may also be scraped physically. This is a mechanical scraping to reduce the contaminants. Further, if we want to reduce the contaminants more, the sample surface is bombarded with energetic inactive gas ions, argon ions of 3 kilo electron volt is bombarded on the sample, and approximately up to 3 to 4 angstrom layer can be etched with this bombarding of the ion. This XPS technique could cause damage to the surface, but it is negligible. That's why XPS is a no destructive technique for the material science research. So I have discussed about this sample introduction chamber. You can see this is showing the sample introduction chamber where sample mount is available. It can be seen directly in the middle of the introduction chamber. The sample will introduce through this chamber. It is in contact with the outside environment, and then a vacuum is created because the size of this introduction chamber is quite small. That's why creating vacuum is quite easy for this chamber, where experimental chamber is quite large. So after having a vacuum of 10 to the power minus 8 torr, we introduce this sample to the experimental chamber for further studies. So this is the schematic of X-ray monochromata. All the components of XPS measurement are mounted on the Rowland circle. You can see X-ray anode is placed here, and emitted X-rays are dispersed by the quartz crystal disperser, and then it will strike to the sample. And the emitted photoelectrons are collected by the energy analyzer or detector. In this way, we are measuring the XPS spectrum. This is the side view of XPS system. Initially, first chamber is sample introduction chamber. A sample holder is there. By opening the gate valve of the experimental chamber, which is big one, the sample can be introduced. The sample is mounted azimuthally at 45-degree angle to the incident X-ray. So that X-ray will strike this sample at 45-degree angle, and then at 45-degree angle, the emitted photoelectrons will reach to the CMA. You can see this is the CMA. And cylindrical mirror analyzer or the detector of the XPS spectrum. Then it is further amplified by the electronics attached to the system. Now a little bit about cylindrical mirror analyzer. How this cylindrical mirror analyzer works. The voltage on CMA for core electrons and OJ electrons are different, and the electron follows different loops to travel and reached at channel drawn at different plates. Okay, you can see by having elliptical path from sample, the ejected photoelectrons are traversing. For OJ electron, there is a separate window is given, and for normal photoelectrons, slit S1 and S2 are given. And on channel drawn, we can specify which electrons are XPS electrons and which electrons are OJ electron. If we want XPS signal, the OJ electron intensity is suppressed, and we can record XPS spectrum after amplification by electronic circuit, which have amplifier, pre-amplifier for noise reduction and other electronic parts. If you want to measure OJ spectroscopy, then XPS component of photoelectron will be slowed down or reduced intensity, and then we can have the OJ spectroscopy. So now I am going to summarize the how this XPS technology works. Initially, a monoenergetic X-ray beam strike on the sample surface that can be of either of two categories for conventional X-rays, aluminum K alpha or magnesium K alpha photon, where for synchrotron radiation XPS, synchrotron radiation is the source. The X-ray photons penetrates up to a few micrometer surface of the sample of around top 10 to 100 angstrom. Ultra high vacuum is required to further remove or eliminate surface contamination. CMA measures the kinetic energy of emitted electrons. The spectrum plotted by the computer from the analyzer signal. The binding energy can be determined from the peak positions and the elements present in the sample can be identified. So this is the binding energy equation, where kinetic energy of electron can be derived from the incident photon energy by subtracting binding energy and spectrometer work function from X-ray photon energy. We can have the kinetic energy of emitted photoelectron. This equation will calculate the energy needed to get an electron out from the surface of the solid. So knowing kinetic energy, incident photon energy and spectrometer work function, we can determine the binding energy of electron. And XPS spectra is a plot between electron intensity and binding energy, where peaks represents absorption at particular binding energy for elements core level. Small broad peaks after core peaks can also be seen. These are known as OJ peaks. Here you can see, if we are going to plot our XPS spectrum with the intensity of electron to the binding energy, then binding energy is increasing from right to left because it is of negative sign. If we are going to plot our XPS spectrum with the intensity of electron and kinetic energy on the x-axis, then kinetic energy increases from left to right. Both are opposite to each other. So now how this XPS spectrum can be interpreted? And we have already discussed about the noise. Noise is actually continuously increasing in the sample. You can see electron collide with other atomic electrons from top layers, decreasing their energy to contribute to the noise at lower kinetic energy than the peak. So they are just giving the noise signal. The background noise continuously increases with binding energy because the sum of all noise is taken from the beginning of the analysis. Initially, if noise is N1, then N1 plus N2 will be the noise for the next peak, and then N3 will be adding for the third peak, and so on. The noise is continuously increasing. So it is of increasing order. Now XPS spectrum. In this XPS spectrum, all the peaks which are generated from the core levels are very sharp. In XPS graph, it is possible to see OJ electron peaks, which are broad peak after the core electron peaks. The OJ peaks are usually wider peaks. The ejected electrons from depth greater than 10 nanometer have a low probability of leaving the surface without undergoing an energy loss event and therefore contributing background signal. So finally, this is our XPS spectrum. This XPS spectrum is recorded with magnesium K alpha source. It is also important that which source you are using, and according to that source we have the binding energy lookup table, and we can see which peak is coming at which binding energy. So oxygen 2s, aluminum 1s, carbon 1s, oxygen 1s, oxygen OJ, you can see These are all the parts of the XPS spectrum. You can see that the noise is also continuously increasing. This is the experimental spectra of the XPS spectrum. Now XPS energy scale. The XPS instrument measures the kinetic energy of all collected photoelectrons. These electron signal includes contributions from photoelectrons as well as OJ electrons. The energies of the photoelectric lines are well defined and quite sharp in terms of the binding energy of the electronic state of the atoms, and OJ lines you can see as broad peaks. So these kind of tables we have for every periodic element. Initially for hydrogen you can see 1s. For K shell energy is given. For helium 1s energy is seen. For lithium 1s energy is there. For beryllium and so on, for all these samples we have whatever shells we are going to receive for 1s, 2s, 2p half, 2p 3 by 2, 3s, 3p half, 3p 3 by 2 and so on. All binding energies are known for every element and it is available as XPS lookup table. This table is known as XPS lookup table. For a particular peak in XPS spectrum, you can check energy in this table to identify for which element it is for, and also we can identify the core level of the element. All values are given in electron volt units in this table. However, for few elements, core levels are going to overlap in the XPS spectrum because of slightly similar binding energy. So here you can see that carbon 1s, argon 2p and rubidium 3p are overlapping because of their slightly similar binding energy value. Carbon appears at 284.2, where argon appears at 248.4 and rubidium appears at 248.7. So these peaks are going to overlap. But by expertise and after few analysis, we can identify these peaks easily. Also depending upon our material selection. If there is no rubidium in our sample, then how we can have a rubidium peak? And if there is no argon in our sample, then how we can have the argon peak? So these peaks can be avoided and we can easily identify the data. The XPS spectra for binding energy refreshing also depends on the sample properties, whether our sample is conducting or insulating. The Fermi level matching of the sample and spectrometer are there for conducting sample only. Here you can see that sample and spectrometer, they have common Fermi level. Because the Fermi level of the sample and spectrometer are aligned, we only need to know the spectrometer work function to calculate binding energy. For conducting sample, the detected electron energy can be referenced to Fermi energy of the spectrometer directly. But when we are using the insulating sample, that electrons accumulation on the surface of a spectrometer raises the Fermi level of the spectrometer. And this increment of the Fermi level can be seen here. It is by ECH value. This blue line of Fermi level and this blue line of the spectrometer Fermi level are separated by ECH potential. Okay. And hence for Fermi level matching between sample and spectrometer, a potential ECH have to be applied, or electrical calibration of the instrument is required if available. Hence, for non-conducting sample, the problem of energy calibration is significant and we need to reference the binding energy with this formula. Here you can see that binding energy can be given by H nu, it is the incident photon energy minus kinetic energy of the collected photoelectron minus work function of the spectrometer minus ECH, which is surface charge energy. This can be determined by electrically calibrating the instrument to the a spectral feature. But if this facility is not available, then by referencing the energy value for fixed binding energy elements, we can shift the XPS spectrum for the change in fixed binding energy values of carbon 1s. It is always at 284.2 electron volt. It is not influenced by any chemical reaction. and for gold. That's why it is a very precious metal. 4f7 by 2 is always appears at 83.7 electron volt. By then we have to put these samples inside the experimental chamber so that we can have the peak from these XPS spectrum for carbon and gold can be recorded to correct the binding energy position of the XPS spectrum. Now, after taking the XPS spectrum, we have to do the data analysis to separate out the important information from the XPS. XPS is a quantitative technique in the sense that the number of electron recorded for a given transition is proportional to the number of atoms at the surface. The peak intensities measured from samples are repeatable to good precision. Okay, if you are going to collect XPS spectra again on your sample, that will be quite similar to that one that was previously recorded. So there is no doubt in XPS spectra. The first issue involved with quantifying XPS spectra is identifying those electrons belonging to a given transition. For this selection of a good background algorithm approximation is quite needed. Initially, peak area is computed from the background subtracted data. It forms the basis of elemental quantification. If the sample varies in composition with depth, then the kinetic energy of the photoelectric lines alters the depth from which electrons are sampled. And in this way, we can measure the depth up to which X-ray photon is penetrated can be measured. All peaks in XPS data have to be analyzed due to ejection of the electron by a direct interaction with the incident photon. OJ peaks are need not to be analyzed. Now, this figure you can see, all this spectra you can see in this figure is recorded for silicon 2p core level. So figures show a sequence of silicon 2p spectra measured from the same silicon sample at different angle. We have already discussed that sample should be mounted azimuthally in the XPS chamber. It means it should be always at 45 degree with respect to the incident X-ray photon as well as collection of the photon by the detector. It should also be at 45 degree angle with reference to the detector axis. If we tilt the sample with respect to axis of the analyzer, it results in changing the sample depth for a given transition, and data collected at different angle vary due to differing composition with depth. You can see at 30 degree, both peaks appeared in the silicon 2p are having the same height, where at 50 degree, the peak appeared around 100 is having more intensity. At 70 it is increased, at 90 it is maximum. So why this happens? So we can see that at 30 degree angle, because it favors the topmost oxide layer of the silicon. So basically silicon oxide is there and there is no interaction with the elemental silicon in this silicon substrate. So both peak have similar intensity. Silicon as well as its oxide have similar intensity. As soon as we are approaching to the 90 degree angle, then the elemental substrate becomes dominant. And in this case, silicon element peak will gain more intensity compared to silicon oxide. Sample roughness, if our sample is not throughout plane, then ejected photoelectron can deviate from its path. This will also affect the peak position and peak FWHM. And the angle of the sample to analyzer also changes the relative intensity of inhomogeneous samples. That's why sample preparation and mounting is very important for recording the XPS spectrum. So XPS measurements are quite significant to these errors. Otherwise, it will influence the quantification value. Here we can see that how this binding energy shifts. And for this, having the chemical shifts point charge model we can use. The binding energy for ith atom can be given by binding energy if atom is available in isolation plus weighted charge of Qi on the ith atom, as well as the potential that is going to influence this ith atom because of the other surrounding charges. So whenever we dope this material element in some material, then this element is going to have change in the binding energy value because of the chemical shift. Like we have seen that silicon elemental peak appears at around 100 and silicon oxide peak is at higher binding energy value. Here also you can see one figure can be shown. The chemical shifts seen in XPS data are also a valuable source of information about the sample. This spectra and figure you can see is recorded on the germanium sample, and this illustrates the separation of elemental germanium and oxide peaks separate due to chemical state. So germanium oxide peak appears around 1454, where germanium elemental peak appears around 1458 electron volt binding energy values. Energy value here. These chemical shifts can also be due to electronegativity effect. Like in carbon oxygen bond, oxygen is more electronegative, so electron oxygen atom attraction will be more, and in this case the peak is shifted to higher binding energy. There are other factors which are also affecting the XPS spectrum. These are electronic effects because of the spin orbit coupling. In your atomic classes, you have studied about whenever a single electron or two electrons having their L and S separately, they are going to contribute towards LS coupling and JJ coupling. So in LS coupling, if L is 0, S is half, there will be single J value half. So the electron emerge from the final state with kinetic energy, which includes the subshell with unpaired electrons. The spin orbit coupling or LS coupling of the orbital and spin angular momentum results in splitting of the energy levels. But here, if L is equal to 0, only a single peak can be seen. So carbon 1s because of the spin orbit coupling. That's why it is always selected as NF for energy referencing. Hence, for a single energy level for a final state, it can splits into two states or more states, referred as doublet pairs, each identified with three quantum numbers N, L, and J. So here we can see only one peak for L equal to 0 condition because we are looking at the carbon 1s spectra. Now we are going to look other spectra also. For copper 2p spectra, you can see L is equal to 1 because it is for P, S is equal to half, so J values will be half and 3 by 2. Accordingly, we will have 2p 3 by 2 and 2p half with a separation of 19.8 electron volt in terms of binding energy. This will remain fixed. However, with certain other element doping, it is going to change also. Now for d orbital, for argentum or silver 3D spectra, you can see the two values of J values are 3 by 2 and 5 by 2 with a reduced separation. So if L value is increasing and corresponding J values is increasing, in that case, the separation between two peaks is reducing. It is up to 6 electron volt only. Now we will consider the case of F electrons. In F electron for Au4F, however it is splitted, but 4F 7 by 2 is never going to change its energy value. It is around 83.7 always. For L equal to 3 and S equal to plus minus half, J values will be 5 by 2 and 7 by 2, and accordingly we have the two peaks. In that case, with a reduced separation of the 3.65 electron volt. Now, after this spectral lookout, we have to quantify the XPS spectrum. XPS spectrum representing the number of electrons that is of energy includes both a contribution from background signal and also resonance peak characteristics of bound states of electrons in the surface atom. So these spectra are quantified in terms of peak intensities and peak position. I am audible to everyone?
Yes, sir.
Yes,
Okay.
sir.
Because it is written here your internet connection is unstable. That's why I ask.
No, it is okay. Perfectly okay, sir. You can continue.
Yes, sir. Yes, sir.
So here you can see in the lowermost figure XPS survey scan is shown. The peak intensity measures how much of a material is at the surface. This survey scan represents the surface is characterized using a quantification table based upon values computed from regions. We have labeled this survey scan for different elemental peaks you can see by looking at the binding energy lookup table. These peak position indicates the elemental and chemical composition. By the intensity, we can reference out by averaging over all peaks how much element is present on the surface. The full width at half maximum is also the indicator of chemical state changes and physical influences. This FWHM changes because of the broadening of the peak may indicate a change in the number of chemical bonds contributing to the peak shape, a change in the sample condition or differential charging of the surface. You can see that in the rightmost corner, down corner, spectrum is shown where peak area is only classified after subtracting the background. That background we need to initially subtract from the XPS spectrum for every peak. And then after removing this noise, we can use peak area to quantify the elemental composition as well as other information. So how we are going to compare sample? In this figure, you can see that aluminum 2s metal peak is there, aluminum 2s oxide peak is there, and copper 3s peak is there. Okay, so these peaks appeared as a single peak in the XPS spectrum, and we have to deconvolute the Gaussian or Lorentzian spectra in these peaks to separate out various ratios. So that's why an XPS spectrum is a combination of number of electrons leaving the sample surface and the ability of the instrumentation to record these electrons. So here you can see that all these three peaks appeared at slightly similar binding energy. So we have to separate. And an XPS spectrum includes multiple transitions for each element also. So one peak is at certain binding energy, other peak is at other binding energy, and so on, which may frequently leads to interference between peaks and therefore introduces the need to construct peak models. And these peak models includes Gaussian and Lorentzian line shapes. And by deconvoluting these peak into several peaks of Gaussian or Lorentzian or combination of both, we can find out the different compositions respectively. Now this is, I am showing some work from our published paper. This paper is published in Global Challenges, a Wiley publication in 2019. Recently, we have included the XPS work in this work. However, we are also performing the X-ray absorption spectroscopy work, but one student is working on the XPS, another student is working on the XAS. It is very difficult to simultaneously learn both technique. In my PhD, I have learned XAS, and after my PhD, I learned this XPS technique. So in this paper, we have studied electronic structure and room temperature ferromagnetism in pure cerium oxide sample as well as gadolinium doped cerium oxide sample nanoparticles. For hydrogen generation, we have tested the photocatalytic water splitting for hydrogen generation using this compound. So you can see this first figure, which comprises of 6 figures, is actually cerium 3D profile, and all data are presented in this 6 figure are background subtracted cerium 3D levels, and different component of cerium can be evaluated by fitting the Gaussian spectra in this. You can see there are so many peaks of blue and green color. They are used to separate out the oxidation states of the cerium. And with this, we can infer that cerium is available in +3 as well as in +4 state, as well as we can determine the X. Here we have represented as X. It is actually representing cerium oxide, CEO2 minus delta. So 2 minus X we have written, and this X is measured also. How much oxygen is going to be removed from the sample, that we can also calculate. In case of nanomaterial, this is the case. So no nanomaterial is of perfect geometry. It is actually CEO2, but it never be CEO2. It is always 2 minus X, and that X we can also calculate from the analysis, where percentage of cerium +3 is calculated from the peak area of the different Gaussian fitted, and percentage of cerium +4 is also evaluated. Now second figure, which is below this cerium 3D figure, is deconvoluted oxygen 1s XPS spectrum. It is also background subtracted and fitted with 4 peaks. Here you can see that OL can be seen, that is the lattice contribution of the oxygen. It is actually sample oxygen. Then OV is shown. These are not in the sample. Oxygen left these site because of incorporation of other elements. Here we have doped gadolinium, and we also have contamination peaks in third and fourth Gaussian, where third is actually the surface oxygen, which is because of the contamination, and the fourth peak is also there because of the hydroxyl group present in the sample surface. So we can also devise the various components with the oxygen 1s spectra. So we have taken out the percentage oxygen lattice, we have taken out the percentage oxygen vacancies, and OH group species are available at which energy value that we have calculated. And all these results are finally related to room temperature ferromagnetic properties of these samples, as well as they are also explaining the photocatalytic water splitting properties of the material. This is our another paper on Fe doped cerium oxide. I have included only 2 because one is with rare earth doping, another is with transition metal doping. Here cerium 3D and oxygen 1s spectra are shown with the magnetic results. You can see that with 5% doping of Fe, slight increment of the MH curve can be seen. MH curve initially, which is black, is actually pure cerium oxide curve. Pure cerium oxide by nature is diamagnetic. It is showing diamagnetic behavior, but it is slightly dominated with ferromagnetic part. But in this red color MH curve, you can see clear indication of ferromagnetic curve. Ferromagnetic MH curve is always show hysteresis loop. So with 5% Fe doping, cerium oxide becomes perfectly ferromagnetic at room temperature. So with this paper, we are able to explain the Fe doping in the bulk cerium oxide sample. Here, cerium oxide sample is in bulk state. But when we use nanomaterial cerium oxide, it always show paramagnetic dominated, very weak ferromagnetic behavior, not diamagnetic. So finally, XPS technology, it is a non-destructive technique. Whatever sample you use in this technique to record the spectra, it can be used for other measurements also. It provides information about surface layers or thin film structure. What are the application of XPS? Applications in the industry. It is also useful in polymer surface, catalyst we have performed the application, corrosion we can use for this application, adhesion, semiconductor industries, dielectric materials, electronic packaging, magnetic media, thin film coating, etc. Two more applications I have shown just to show the importance of the XPS analysis. Initially, it was believed that pigment from mummies, this is a Egyptian mummy on the left hand side of the figure. This mummy is considered to be wrapped by Fe2O3. But when XPS analysis is made on this wrapping, it is found that Pb3O4 is used to wrap the mummy instead of Fe2O3. Even when we are analyzing the solar energy collectors, you can see this is a solar cell on the first left side figure, and it is always mounted by the conductive oxide, stannous oxide layer. This stannous oxide layer should be equally mounted on the complete solar cell layer, solar collector layer. So if you can see the XPS profile, you can see that initially stannous oxide, because of the small quantity of the stannous oxide, it is mounted in decreased amount compared to the outer side of the collector. So by which we can see that stannous oxide mounting is not uniform on the solar collector surface. This we can also check. Thank you. So now this talk is over. I would like to thank Dr. Suresh T. Silawat, Principal of the college, Dr. G.D. Gupta, Convener, Head and Professor Physics, Dr. R.C. Gupta, Professor and Co-Convener of this webinar, and Dr. Netram Kaurav, my friend, Organizing Secretary, to invite me to deliver this lecture. However, I tried to discuss this presentation in very basic physics and basic science, but probably it will be difficult for others to understand. But in case you want to use this technique for your research, then you can talk to me personally also. Thank you, sir.
Thank you, sir. We have some questions from the participants.
Okay.
One participant is Ketan Desmukh. He has raised question that what kind of data XPS would produce on core cell S and BI, or it is TEM?
S and VI.
S and BI.
Okay. Sulfur and bismuth.
Yeah.
We can have sulfur at 2p level and bismuth 4f levels, important for these core level spectra. And we can study about the bismuth presence in different oxidation state, and if there is a compound in bismuth and sulfur, that can be easily proportionate contribution of these compounds can also be seen.
Yeah. Another question is Dr. Jadhav. How photoelectron and agar electrons are separated in XPS machine?
We have seen that these electrons are collected on the chalendron. Okay, and this chalendron have the intensities recorded for the XPS as well as OJ. But if we are going to record the XPS spectrum, the intensity of the OJ electrons are suppressed, and it can appear as a broad peak, where the core electrons are showing the highest intense peak. So they can be seen separately.
Yeah, there is one more question. Can we this is from Sagar Sen. The question is, can we calculate energy levels or spin orbit level split of any element by theoretical assumption, because different element and compounds have different splitting, and another is how splitting affected by metal oxide and only element.
Yeah, this is a good question, and chemistry people are calculating the energy level separations or energy level diagram or band structure diagram using this XPS techniques, and we can directly look the impurity levels also, which are contributing to the electrons nearer to the conduction band. And in case of acceptor impurity, these impurity levels are created nearer to the valence band, and all this electronic level diagram can be created with the XPS spectrum analysis. It can be done.
Yeah, this is the last question, because the participant is Divya, and her question is, in photoelectric effect, how the electron is ejected? Hello. Hello. I think the speaker is signed out somehow. So, Dixit sir, let us end the.
Thank you very much to all participants, and also Dr. Saurabh Dalal sir for sparing time to deliver this lecture. It is very informative and very good lecture for us. I think all the participants will benefit it with this lecture. We will hope so. And tomorrow at 10:30, we will be again on another lecture. So thank you very much.
All participants are requested to fill the Google form for the attendance, and I have left many questions, so I will forward all those questions to the speaker, and he will give you the answer for all the questions.
One more thing, Dr. Kaurav sir.
Yes, sir.
Ask him to share this PPT
Yes,
at
sir.
your mail,
Yeah.
so that if anyone wants to check it or want to read it,
Yeah.
then that can be given to them.
Okay, sir. We can do that too,
So
for all the
thank you.
participants.
Thank you very much.
So thank you for all. I'm just ending.
Dr. GD Gupta is on. Boss, unmute करो. बॉस ऑन तो हो, अनम्यूट करो. चले गए इसका मतलब. चलिए ठीक है इतना.
नहीं है, जीडी गुप्ता सर
है लेकिन उनको अनम्यूट.
हाँ, हो गए.
Yes, boss.
Yes, sir.
Thank you.
Okay, sir.
With your leadership, the second lecture is over now.
Thank you, sir.
कल अपन तीसरे लेक्चर का शुरुआत करेंगे.
Yes, sir.
Thank you very much.
Okay,
Thanks
okay.
to all.
Okay, thanks for core team for